All right, so we're going to do another example of type 1. But this time, we're going to look at an example that doesn't converge, so that the area underneath the curve is not finite. So let's go from 1, let's change it. Let's go to 2, from 2 to infinity. And last time we did 1 over x cubed, so let's do maybe 1 over x. And what we want to keep in mind too here is there's this phenomenon that happens with these negative powers of x, where there's some boundary where all the powers above some value of x on the bottom of a fraction are going to have finite areas, and all the values below some value as a power of x on the bottom of a fraction is going to not converge. It's going to be infinite. And so here's one of those boundary cases, and then we will look at, or I'll at least post a slide about explaining why this is the boundary and what that means. Okay, maybe not a whole video, but okay. So here's our example. We're going from 2 to infinity. So maybe let's draw a picture of this also, just to get an idea of what this looks like. So on the domain we're interested in, 1 over x looks like this, and of course over here does the same thing. And we're going from 2 to infinity. Infinity we think about being way out here. And so the question, again, just like the last one, is as our function goes out to infinity on the right hand side, is it dropping down low enough, fast enough, in order for us to get a finite area? And the answer is going to turn out to be no in this case. Well, let's see how that works. We're just going to apply the definition again. We're going to replace infinity with the letter b, which we'll use as a sort of dummy variable, and then we're going to take the limit as that variable goes to infinity. Okay, so let's do that. So come over here. We're going to take the limit as b goes to infinity. We're going from 2 to b, 1 over x dx. And there's no reason to write this as a negative power of x, because we can't use the power rule in this case, right? So this is one of those one-off integrals. There's no family of integrals we can just sort of apply a rule to. Remember that the antiderivative of 1 over x is just the natural log of x. And it's just natural log of the absolute value of x, but we don't have to be too careful with absolute values, because all the values we're plugging in are going to be infinity. So let's do this. So we're going to take the limit as b goes to infinity. The antiderivative of this is the natural log of x, and we're going from 2 to b. We're going to take the limit as b goes to infinity, and now plug the values in. So natural log of b, we know b is positive, so we don't need to worry about the absolute value, minus the natural log of 2. 2 is also positive, so we don't have to worry about the absolute value. Okay, so then the question becomes, what happens here, right? Because this is, the natural log of 2 is a constant value. It's an irrational number. We don't know what it is, but it's not changing. But what happens to the natural log of b as b goes to infinity? Well, the answer is it goes to infinity. So the natural log is as an increasing function everywhere. It's one of the slowest increasing functions, so it increases very slowly, but it does increase forever. And so the answer to this really is infinity. And so we're going to call this divergent. But really what's happening is that this thing isn't dropping down fast enough, and so the area under this is actually infinite. And so instead of adding just further and further down the decimal places, we're actually adding a good meat to the place values ahead of what we're doing, enough so that this area is actually going to infinity.